Welcome back to part 2 of lesson 3. Today we're going to review quantum numbers and then examine how to write electron configuration of atoms. Let's recap the quantum numbers. So there are 4 quantum numbers. The principal is the first one. Principal quantum number represented with n. That represents the energy level or the distance from the nucleus. The possible values are 1, 2, 3, 4 to infinity. The angular momentum number, or the L, also known as the shape number, represents the shape of the orbitals with the value 0, 1, 2, 3, or SPDF orbitals that we looked in the previous lesson. The magnetic quantum number is represented with the letter ML. Indicates the special orientation of the orbital with respect to a 3D. So for the 0 is for S, minus 1, 0 plus 1 is for P, minus 1, minus 2, minus 1, 0 plus 1 plus 2 is for D, etc. So this would represent, for example, this is the P orbital representing the Px, Py, Pz. The spin quantum number is represented with the letter Ms, and thus the direction of the electron as it spins on its own axis. The possible values are plus half or minus half, indicating the direction of the spin, clockwise or counterclockwise. So to write quantum numbers for any electron, we have to, let's start with the simple case of hydrogen. Hydrogen has a single electron. The 4 quantum numbers are indicated here, the N, the L, the ML, and the MS. The numbers would be 1, 0, 0, plus half. It gets a bit more complicated when we have atoms with many electrons. This is the case of the sodium atom, for which we have 11 electrons. The key factor here is always to remember the possible values. So n is a positive integer from 1 to infinity. N is 0 to n minus 1. The possible values of ml are minus L to plus L, including 0, and the possible values of ms are only plus half and minus half. So once you do that you remember the possible values, you'll be able to write it correctly. What I want to point out here is in the case of the 2p electrons, we have 6 electrons in those p orbitals, px, py, pz. So many textbooks alternate between positive and negative values for the ms, which is okay because give you the same answer. Or you can start with the positive values followed by the negative values. That way you obtain. Practice a little bit more with atoms that have more than 11 electrons to see how well you fare with writing those quantum numbers. Let's answer some review questions to wrap up. If n equals 3, what are the possible values of L? 0, 1, and 2. Remember, all you need to apply here is L is equals, the possible values are 0 to n minus 1. So n minus 1 would be 2. What are all the possible values of ml? So you have to consider for each value of L. So if L is 0, this is 0. If L is 1, it would be minus 1 to plus 1. And if L is 2, it would be minus 2 to plus 2, as shown over here. What are the possible values of ms? So ms has only 2 possible values, plus half and minus half. If n equals 2, how many types of orbitals are there? We have 2. We have an s orbital and p orbital. How many actual orbitals are there? We have 4. We will have a 2s orbital, the 2px orbital, 2py, and 2pz. So a total of 4 orbitals. Now let's consider when n changes. So now n is 3. If n equals 3, how many types of orbitals are there? We have 3 orbitals. We have now the s, the p, and the d orbitals. And how many actual orbitals are there? You name them. So these ones we would have a total of 9, starting with the 3s, followed by the p, px, py, pz, the 3. And then the 3d, we have 1, 2, 3, 4, 5 different orientations for the d. So the names would be 3dz2, 3dx2y2, 3dxy, and 3dxz, 3dyz. So this is the end of the recap. I will be writing up little exercises for you to practice more how to write those quantum numbers. with regard to electron configuration, let's talk about what is meant by that. So you have a computer, you need to configure the computer, means to get it ready to do what you want it to do. So in order for us to understand chemistry well, we need to write electron configuration. We need to show the arrangement of electrons in an atom. There are specific rules in order to write those electrons in an atom correctly. There are 3 rules to be specific. The first rule is called the off-bow principle, that it states that electrons occupy the lowest energy orbital available. The second rule is the Hans rule. This one states that electrons being added to orbitals with the same energy and shape, what we call degenerate orbitals, they occupy one orbital at a time before a second electron is added. And the last rule is the Pauli exclusion principle that says not 2 electrons can have the same set of 4 quantum numbers. Let's examine the first rule, the off-bow principle, in a more descriptive way. So that says that we are going to add electrons in a specific order. The order is based on the relative energies from the lowest energy orbital available to the highest energy orbital available. So we start filling these orbitals here first. This represents the 0, 1, 2, 3, 4, the s, p, d, and f orbitals. Notice that the sequence is not in a mathematical order. So first we start with 1s, followed by 2s, 2p, 3s, 3p. Notice here the first overlap. 4s comes before 3d. Continue. Then 3d is followed by 4p. 5s comes before 4d. So we have a second overlap. To help students remember these overlaps, there's a mnemonic that you can apply, and it's shown on the right hand side here. So the mnemonic is called the diagonal rule. You can write it like this, practice many times, where you write these numbers, and then you eventually, with this approach, you can write the electron configuration of any atom. Once you fill these ones, for example, that means that you fill the 1s, so it will be 1s2. The superscript indicates the 2 electrons that can be added to the s orbital. Then this is the electron configuration for the element lithium that has only 3 electrons, 2 plus 1, 3. So we have a full orbital fill, the 1s, but the 2s is half fill. So this electron here is what we call the valence electron, because it's in the outermost energy level that we find the valence electrons. So the electron configuration will help us so much to define the number of valence electrons if you don't have a handy periodic table to figure out that, or if you want to figure out what would be the location of an unknown element using the electron configuration. I would say this element is in row 2 because it's in the second, the energy level, the highest energy level specifies the row or the period, and the number up here, the number of valence electrons, that specifies the column. So it's in column 1, period 2. Let's examine more in detail the other rules and the way to write the electron configurations. So there's different standard ways to write the electron configuration. One is called electron configuration notation, or ECN. The other one is called the noble gas. And the third one is called the orbital notation. This one uses arrows to represent electrons. So here we have hydrogen. In hydrogen, we have this box represents the orbital 1s. That takes 1 electron. So this part in here is your ECN, electron configuration notation. If I write a line with an arrow on the top and the numbers 1s, that would be your orbital notation. So imagine this box, but without the box, use the lower line and the arrow with the type of orbital underneath. That describes the orbital notation. So let's examine the first 6 elements in the periodic table, from hydrogen up to carbon. So noticing here that then helium is the next element in the periodic table. It has 1 more electron, so you start up and then down, and following Hans' rule. These are orbitals, so we're adding electrons 1, and then the second one down. Different spin, that these numbers up and down represent the different spins. Then in the case of lithium, we have 1 more orbital available, the 2s orbital. So it's 1, 2, and then 3 up. Then we get to beryllium that has 4, so 1, 2, 3, 4. Notice here, this is your electron configuration notation. Electron configuration notation. This one is your noble gas notation. It means that we can abbreviate. We can look at the noble gas prior to that element and put it in brackets, and then continue on from that element. Helium, in this case, helium has 2 electrons, so then we got the next one to write the 2s1. The same thing here. We have the noble gas notation for beryllium. It would be helium in brackets 2s2. And the next one is boron, atomic number 5. So we have 1, 2, 3, 4. Then we have 3 orbitals of the same energy, or what they call degenerate orbitals. Same shape, same energy. So these ones are going to take one electron at a time. So in the case, this would be carbon. So carbon has 1 and 2. And if we add one more, we will have the next element on the periodic table, which is nitrogen. So now let's take a closer look at the second rule for writing electron configuration, the Hans rule again. So that rule says that electrons occupy each p orbitals one at a time and with the same spin until half filled. Then the electrons will pair to finish the p orbitals. So what that means, for example, if we were to look from lithium, continue on to neon, number 10. In lithium, we have the 1s and the 2s. So here we add 1 electron, so we get beryllium. Now for the p orbitals, notice that we start adding 1 electron at a time, pointing up. So that means they have the same spin before you put the second electron. So the rule of thumb to follow here is this. You start 1 up, 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 then down, down, down. That's just to comply with the Pauli exclusion principle, that no 2 electrons can have the same set of 4 quantum numbers. If you have 2 electrons pointing upwards, it means they have the same spin and therefore they have the same set of 4 quantum numbers. That's incorrect. And on the right hand side, what you see here is the electron configuration notation. So we have taken here, this is 1s. The 1s has 2 electrons. The superscript shows you the number of electrons in that orbital, and so forth. Let's look at the configuration of the third row elements. So in the third row, we go all the way from sodium to argon, from 11 to 18. So notice again here that we're adding 1 at a time before we add the second one down. So up, 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 down, down, down. And here we have the electron configuration, but the noble gas electron configuration using the previous element, which is neon, the previous noble gas. So that way it's an abbreviated form of that electron configuration. And let's have a look at the 4 row elements. So all the way from potassium to chromium 24 here. So in this case, we start filling the 4s, and then it's completely filled. Then we add to the D, and the D, we have the same situation. We start adding 1 at a time, we add the second one. When we encounter the element chromium, there's an extra measure of stability associated with half-filled and completely filled orbitals. So instead of adding 1 extra electron here, so we have 1, 2, and 3, we would expect to add 4, but we took 1 away from here to put it in here. So that one was taken away from the 4s and added to the 3d to add that extra level of stability. So this is one of the exceptions, chromium, in the 4 row of elements. Also on the 3rd row of elements, if we continue, we have manganese all the way to copper. Is the same situation. The 4s is being filled, and then we start filling the 3d, up, 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 then down, down, down. But here we encountered another situation similar to chromium, another exception like chromium. So this fact that 1 electron from the 4s is taken away and added to the 3d is to add that extra level of stability. So chromium, as we saw here, as well as copper, are exceptions in the way that the electron configuration is written. Okay, so to summarize electron configuration, we can actually use 2 ways to write that electron configuration. One way would be using the diagonal rule that I showed you at the beginning, and that I suggest that you practice a lot, how to write that diagonal diagram, diagonal rule diagram, and the second one is using the periodic table. So let's say, for example, you have a blank periodic table like this one. Notice this is color-coded to represent the different blocks, the S, the P, the D, and the F block. It means electrons are being added to S orbitals, to P orbitals, D or F orbitals. And the number of columns also represent the number of electrons. An S orbital holds 2 electrons, a P holds 6, so we have 6 columns, a D holds 10, we have 10 columns, and an F holds 14, so we have 14 electrons. So imagine that somebody is giving you the following element, germanium. So how would you write the electron configuration for germanium? Germanium is atomic number 32. So you would start by saying the 1s is filled, followed by the 2s, 2p, 3s2, 3p6, 4s2, 3d10, 4p2. And that's exactly what we obtained here. This is your electron configuration if you follow that order. Now you can abbreviate it by using the noble gas notation. So the previous noble gas to germanium is argon here with atomic number 18, and then followed by what is left. In some cases, this electron configuration is rearranged. Notice this is what the diagonal rule will give you. 4s2, 3d10, 4p2 is rearranged to write 3d10, 4s2, 4p2 to locate with much more ease the valence electrons, the electrons in the outermost energy level, the 4 energy level. So we have 4 valence electrons for the element germanium. Let's stop here, and in the next lesson we're going to practice a little bit more on how to write these electron configurations and introduce the new part of this unit, which is the Vesper theory of molecular geometry. Thank you.